everyone, welcome to today's lesson. Today we are introducing nuclear chemistry, an area of science which we have harnessed for purposes which range from energy production to warfare to cancer therapy and beyond. In today's lesson we are going to be revising the structure of the atom, introducing radioactivity and describing three types of radiation. Hopefully at the end of the lesson you will be able to define radioactivity and describe various sources of radiation, as well as describing alpha, beta and gamma radiation in terms of mass, charge and something called penetrative power. Now, before we get stuck into revising the atom and introducing nuclear chemistry, it is important that we remind ourselves where elements come from. Now, elements are created in the stars from simple elements. For example, if two hydrogen atoms come together, they fuse and produce helium and release energy. This process is something that we call nuclear fusion. So let's just remind ourselves of the structure of the atom, something we have covered before. Inside the nucleus, we have protons and neutrons. Now, protons have a charge of +1, they are positively charged, and they have a mass of 1. Similar to protons, neutrons also have a mass of 1. However, they have no charge, they are neutral. Outside of the nucleus in electron clouds, we have electrons. These are negatively charged particles with a mass of roughly 0. Now, each element has an atomic number, and this atomic number represents the number of protons inside the nucleus. As well as having an atomic number, they also have a mass number, and the mass number is the number of protons plus the number of neutrons. Now, isotopes are something that we covered in Unit 1, and it's something that is going to come back up as we discuss nuclear chemistry. Now, isotopes are atoms which have the same atomic number but different mass numbers, or they are atoms with the same number of protons but a different number of neutrons. Now, the atoms of most elements will have isotopes. Now, we can use nuclide notation, which gives us the element symbol, the mass number and the atomic number, to compare one element to another or to compare isotopes to one another. Now, from the two numbers that nuclide notation gives, the number of protons and neutrons can be calculated. Now, in front of us we have uranium. It has an atomic number of 92. In nuclide notation, our atomic number is on the bottom. It has a mass number of 235. So in nuclide notation, remember we have our symbol, our mass number, top left, and our atomic number, bottom left. We can work out the number of protons simply from looking at the atomic number, it's 92. And our number of neutrons, to work that out, we take our mass number, which represents protons and neutrons, and take away our atomic number, which is only the protons. So 235 minus 92 gives 143. So in this atom of uranium, there are 92 protons and 143 neutrons. Protium, deuterium and tritium are isotopes of hydrogen. Now, we can write their protium, deuterium and tritium are isotopes of hydrogen. Now, hydrogen is unique in that each of its three isotopes all have their own names. Now, what we can do, so you can see the difference shorthand between the three, is we can write the nuclide notation for each isotope. Now, all three will have the symbol H for hydrogen, as they are all hydrogen atoms. Now, protium has 0 neutrons and 1 proton. Now remember, our number of protons is our atomic number, and it goes on the bottom left. And our mass number, which is top left, is neutrons and protons added together. So protium, which is the most common atom that makes up hydrogen, has the nuclide notation 1, 1H. Deuterium would also have an atomic number of 1 because it has 1 proton. It would have a mass number of 2 as it has 1 neutron and 1 proton. We add those together to get 2. Our last example, our last hydrogen isotope, is tritium. It has an atomic number of 1 because it has 1 proton. Our mass number will be neutrons and protons added together, so it has a mass number of 3. Now remember, when we are writing nuclide notation, our mass number is at the top and our atomic number is always at the bottom. Now, as we move through that periodic table, the ratio of neutrons to protons increases. And as it does so, as we add more and more neutrons to a nucleus, it becomes very unstable. Now, unstable nuclei are described as radioactive, and they contain a lot of energy. Now, they release this energy in the form of particles and rays in order to become more stable. And this is called radioactive emission. So, radioactive nuclei release particles and rays in order to release energy and become stable. And this is the process of radioactive emission. And there are 3 types of radioactive emission: alpha, beta, and gamma. Radioactivity is something that is all around us, and that which is all around us is called background radiation. So there are a lot of natural sources of radiation. Cosmic rays, which is radiation that reaches the Earth from space, such as the radiation that comes from the sun. Within our Earth itself, we have some rocks that are radioactive and they give off radioactive radon gas. Our plants, our living things, are able to absorb radioactive materials from the soil, and these then pass up the food chain. So plants absorb radioactive material from the soil, animals eat the plants, we eat the animals, and in this process radiation is passed up the food chain. Now, for most of us, our background radiation dose will consist mostly of these natural sources. However, it's important to note that there are a number of man-made or artificial sources which exist and could be contributing to your background dose, such as radioactive waste from nuclear power stations, radioactive fallout from nuclear weapons testing, and medical X-rays. Artificial sources, such as those described here, account for about 15% of the average background radiation dose, and nearly all artificial background radiation will come from medical procedures such as receiving X-rays for X-ray photographs. So the radiation we are exposed to every day, 15% of it comes from background radiation. However, very little of that is the result of radioactive fallout or radioactive waste. The vast majority is from medical X-rays, unless, of course, you live on or around somewhere such as Chernobyl. So as we have said, there are three types of radiation. Now, the process by which our unstable nuclei release energy to become stable is called nuclear decay. And they release energy either in the form of alpha, beta, or gamma radiation. Now, our alpha radiation can be represented by the symbol alpha 42 or helium 42. And that is because the release of from its nuclide notation, we can say that it has a relative mass of 4. Its charge is plus 2. It is the same in nature as a helium nucleus. Our beta particle is similar in nature to an electron, and it has a mass of approximately 0, so 1/2000th of a mass unit. It's negatively charged. Now, our gamma radiation has no symbol, has no mass or charge, and it is released in the form of electromagnetic radiation, which we can also call waves. Now, all three types of radiation will come from unstable nuclei. Alpha and beta are particles, but gamma radiation consists of electromagnetic waves and has no mass. Alpha radiation, or helium nuclei, is made up of 2 protons and 2 neutrons. Beta radiation is made up of electrons. In the nucleus, neutrons break down to form a proton plus an electron. Inside these unstable nuclei, we take a neutron and we break it down into a proton and an electron. So we've got that represented here. So a neutron, which has a charge of 0 and a mass of 1, breaks down into a proton, which has that mass of 1 and a charge of 1, and an electron with a mass of 0 and a charge of -1. Now, we are going to spend a bit more time looking at nuclear equations in our next lesson. However, the key thing is the top number on the left hand side has got to be the same as the sum of the top numbers on the right. So I have 1 on top here, and if I do 1 plus 0, I get 1. So these numbers balance out. It is the same for my number on the bottom. Here it is 0. On my right hand side I have 1 plus -1 also gives 0. So our number on the bottom is the same on the left and the right, as is the number on the top. As I said, we will go into more detail on that in our next lesson. Now, as this happens in our unstable nucleus, these high energy electrons are thrown out of the nucleus at a very high speed. Now, just for the purpose of noting this in your pupil book, we have symbols for each of the subatomic particles. Protons have a charge of +1 and a relative mass of 1. They are represented by the letter P, and the number on top represents their mass, and the number on the bottom represents their charge. For our neutron, it has a relative mass of 1, mass on top, and a charge of 0, charge on the bottom. Our electron, represented by the letter E, has a mass of 0, so we have a 0 on top here. And it has a charge of -1, so we have our -1 represented here. Make sure that you get a note of that in your pupil booklet. So going back to our types of radiation again, they all have different charges and they are therefore deflected differently in an electric field. Now, if we have a source, this is our red box here, of alpha, beta and gamma radiation, and we put them and we pass them through an electric field which has a positively charged and negatively charged end, we will see them deflected in different directions. So our gamma radiation has no charge, so it will not be deflected in either direction. It will pass straight through the field. Our beta radiation, on the other hand, is negatively charged. It will be deflected towards our positive side. Our alpha radiation, being positively charged, will be deflected towards the negative. What you may have noticed is that this beta radiation is more significantly deflected than the alpha particle. Now that is because beta radiation is lighter than alpha. Remember that alpha particles have a mass of 4 and beta radiation have a mass of approximately 0. So based on their mass, there is a greater deflection of beta particles compared to alpha. Now the three types of radiation also differ in something called penetrating power. Alpha particles can be stopped by paper. If you thought there were alpha particles coming towards you, hold up your jotter. Stopped. Can't get to you. Beta particles are stopped by a sheet of aluminium or lead. You can hold up a bit of aluminium foil and beta particle cannot pass through. Gamma waves, on the other hand, can only be stopped by blocks of lead or concrete. They pass easily through paper and that ½ centimetre of lead, and only these blocks of lead or concrete can stop them from passing through. So based on this, which type, alpha, beta or gamma, do you think has the highest energy? The answer would be gamma, and alpha has the lowest energy. So just to summarise that last slide. Alpha radiation is able to travel a few centimetres from where it was emitted through the air and is stopped by paper. Beta particles can travel over a metre from their source and are stopped by aluminium. Gamma, which has the highest energy, travels great distances through the air and can only be stopped by lead or concrete. So that takes us to the end of this short introduction to nuclear chemistry. What I would like you guys to do now is make sure your pupil books are complete and have a go at pages 66 and 67 in your CGP workbooks. If you need any help at all, please don't hesitate to get in touch via email or on Teams. I will get back to you as quickly as I can. So thanks for joining in on this one, guys. I will see you all in the next one. Bye everyone.